It is a pleasure being here in Hong Kong for the Ovarian Club and CoGEN meeting. I would like to welcome you for a highly scientific day and program. And in order to open the Congress, I would like to invite the chairman of the Congress, Professor Milton Leong, to open this meeting.
Good morning, 大家好. It's my honor and pleasure to open this Congress. This is the 10th time of the Ovarian Club and the 3rd time we have it in Asia. And this time we invited also our other brand in the IVF-Worldwide.com, the Virtual Academy of Genetics, which have yearly meetings as CoGEN, the Controversies in Genetics and pre-implantation diagnosis. So it's our aim and our partners' aim. We doing this, with Society for Reproductive Medicine in Hong Kong. We both want to present an education opportunity to bring attendees to this meeting up to date on the most recent advances in reproductive medicine. And also, in this time, I think very different from and additional and different from other meetings on genetics and reproductive medicine, we have added the important sessions of discussing the ethical issues. As science progresses, we think that maybe we need people to remind us that there are human issues and there are social issues. So, so I hope the sessions tomorrow on ethics will also be of interest to a lot of people here. As I said, our aim is to further, and make sure that every year we'll bring to Asia the top speakers in the world. And luckily, they're all our friends. And as you see them, as you meet them today, you will know who they are already. And I'm sure, that you'll get a lot out of the lectures for these 2 days. So thank you for coming and welcome to the meeting.
And the first speaker of this meeting is Professor Marc-André SIRARD. After graduate studies at the University Laval on in vitro fertilization to generate the first clinical method to produce test tube calves in 1985, he went for a postdoctoral training in Wisconsin to study in vitro maturation of oocytes. He came back to Quebec in 1987 and became an industrial chair professor in 1990. He founded the Center of Research Biologique de la Reproduction in 1995, which has grown to include more than 100 people today. He obtained his senior Canadian research chair in 2000 on genomic applied to reproduction and has led the Embryo Gene Strategic Network on mammalian embryos. He has published over 281 scientific papers and has been invited to give over 75 invited lectures in international meetings. His current research activities are focused on the influence of the ovarian environment on oocyte quality in human and large animals. And he will share with us his knowledge and give a talk this morning about how to synchronize oocyte GV2 for mammalian IVM results, for maximal IVM results. Thank you.
Good morning. Thank you very much, Dr. Leong and Dr. Shoam, for the invitation. It's a pleasure to be in Hong Kong again. It's a very nice city. It's very beautiful. And the view is just fabulous from my room, so it's really great to be here. This morning, I'm the first of 3 speakers that have a background in animals where we use some models to study oocyte maturation because it is a good source of material. Animals are much easier to get access. And what I'm going to present this morning is about what we've learned in those animal models that apply to human IVM, and with the objective of trying to improve the capacity to extract good oocytes with good quality out of IVM, in vitro maturation. So it's kind of a mystery what makes a good eggs. In the mouse, all the eggs that are fully grown, they're good. But in cows and in human, that's not the case. Many eggs are fully grown, they can be fertilized, they will not make blastocysts, will not make a baby. So they have to be programmed. And the programming of the eggs start early on in the follicular environment, where the follicle is giving the oocytes a number of instructions. How to become a blastocyst, that encoded mainly in the form of mRNA that is stored in the oocytes. Without those instructions, the oocytes will not be able to pass the 8 or the 4-cell stage and go to a monoline blastocyst. So this information is key. Now what we have to study and understand better is how and when the follicle is giving those instructions to the oocytes, because if we get the oocytes before they give the information, they will go nowhere. We have to organize for them to be ready when we pick them up. So during the growth phase, there's accumulation of the material that is required to become an embryo, but there's also a phase of differentiation when the follicle is big enough, and normally that will happen when we have a dominant follicle, and that information will then be translated into the oocyte's capacity to become an embryo. And during that window of the late follicular growth and the activation of the embryonic genome, there is a period of 5, 6, 7 days where there's no transcription. So the oocyte has no capacity to express new genes. The oocyte must use the information that was stored. And once the storage is finished, the oocyte is kind of stuck or limited by the information it already has. In animal study, we have learned that the competence to become an embryo is not acquired like this. It's not like just one thing that makes this a bad egg into a good egg. It's an accumulation of information, accumulation of making good spindle, making good cortical granules, making the accumulation of RNA to do all the steps post-fertilization, and this is accumulated gradually. If I try to summarize years of animal and human study, we can see on that slide that the follicle that just start to have an antrum and have no FSH receptors, those oocytes have very little, if any, capacity to become an embryo. When the FSH receptor appear at the antral stage, then there's a window where these follicles can produce good eggs, and after that they go often into atresia, or if they grow further and then acquire LH receptor when they're becoming dominant, suddenly the quality of the eggs inside goes from like 20% blastocyst to about 50% blastocyst. And at the end of the day, when the maturation occurs in vivo, or the last day before ovulation occurs in vivo, then there's still another increase in the capacity of these oocytes to become embryos. To try to represent that, I'm using an analogy. It's the apple analogy, because it's really, to me, it's a very good example of what really is happening. When we promote follicular growth with FSH, it's like growing a green apple. The green apple will keep growing but will not turn red, will not be ready until there's LH receptor in the granulose cells that tells that egg, you're going to ovulate. Because normally in human, and the same in my animal model, the cow, only the LH receptor containing follicles will ovulate, and therefore the follicle will give the final instruction only to these eggs that's going to be expelled in the oviduct, so there's no danger for the ovary to have a cancer from those eggs. So in the transition from LH no receptor to LH receptor, then there's a window where that LH is working to change the oocyte's quality. And the window in the natural cycle, so if I show to you a natural menstrual cycle, you have the rise. You don't see the mouse here. So you have the rise and the decrease of FSH, and between the decrease of FSH and the LH surge, so there's a window of 5 days between the decrease in FSH and the LH surge, and in that conditions, that window is important for the oocytes to get the information it's been waiting for. If we do a very simple experiment where we give FSH to, this is a cow experiment, but it's the same ovarian response that you would see in human. If you have a simple experiment where you give FSH for several days and then you stop giving FSH for 1, 2, 3, or 4 days, the follicle will still growing, because like the red one here in this graph, or the one that are larger than 10 millimeters, the one that normally have LH receptor, they will keep growing. But the big surprise is if we look at the quality of eggs during that going up in follicular size, we initially see an increase in quality. This is the rate of blastocysts after stopping FSH for 1, 2, 3, or 4 days. So initially, the quality goes up, and you can even see some animals where the quality is 100% blastocysts you can obtain with those. And then the quality stabilizes for 2 or 3 days, and then the quality goes down. So the oocyte, if it's not ovulated, even in a growing follicle, if it's not ovulated after 3 days of being under LH support, it's going to start to turn bad or sour. And if I use my apple analogy again, it's like when they're still growing, the apple is still green. When they're fully grown and they have been on LH for 2 days, they have a red color, so they're ready to be harvested. But if you wait, then you have this phenotype where the oocyte's quality starts to go down. Now let's turn to human study we've done. Many years ago, we were trying to figure out what were the follicular condition associated with the successful oocyte. So we did the follicular analysis of each follicle from patients and classified them accordingly if they ended up making an embryo or a baby or without any success. So this was done by individual follicular aspiration, where each follicle was analyzed individually, and each oocyte was also analyzed individually. We have published a number of papers on what are the conditions, like the genomic conditions that are associated with success. But what I want to share with you today is the same type of phenotype we observe in animals that now we see in humans. So you can see here the effect of follicular size on the ability of or the quality of embryo. So in the gray on the top, you can see the transferable embryo, and the middle orange is the poor development, and in the blue is the no development. Normally, you would expect, as the follicle grow larger, that you would have a linear increase in the number of transferable embryo. This is not a big group because it's all individual follicle aspirated. So it's not significant, but we don't have neither an increase. We have something that looks more like a decrease in quality with the largest follicle. So that was the first thing we realized, that the human large follicle were similar to the animal large follicle. If they stay around for too long, the oocytes inside might decrease in quality. So that brings us to this concept of the oocyte shelf lifetime, that there's a limitation of the oocyte's capacity to sustain a longer period in a larger follicle. And the reason we think is because the oocyte, they have to shut down their transcription, as I said at the beginning, before ovulation. This is required because the oocyte has to reprogram itself. The oocytes, the embryo does not need a zona pellucida or cortical granule. So all these genes that were active in the oocytes to make those components have to be shut down. The same for sperm. When the sperm arrive, the DNA was set to make a head and a tail, you have to erase that. And to erase the program, you have to shut it down. So the oocyte has no capacity of transcription for such a 4 or 5 days period. And when you have no transcription, your capacity to survive in time is limited. So when oocytes stop making RNA, it has to be ovulated within about 60 hours, otherwise it dies. So back to this slide. Now we're trying to understand what is the timing that is required for oocytes to be ovulated when he has received the right amount of instruction. That is when the follicle starts to have LH receptor. In animal study, we're going to go back to the cow, the mouse, and the goat in this slide to show that these are all GV stage oocytes. These are all immature oocytes at the nuclear level. And you can see that even if they're all GV, when they're getting closer to ovulation, their chromatins start to condense. And in a mouse, they call it non-surrounded nucleolus or surrounded nucleolus. And in the cow and human, we have built another system. It's called the GV123 system. And this is based on the amount of compactness we can see in the oocyte. So you have here A, B, C, D. These are all GV stage, and you can see how different the chromatin will be inside. And this is associated also with the shutdown of the transcription capacity of these eggs. You have here the labeling of transcription, and you can see that the GV0, for example, has a very dark nucleus because there's a lot of RNA being made, while the GV1, it's spotty, and the GV3, you can see it's completely white. So the nucleus is totally silent in terms of transcription. Although these are bovine study, if you look at the human, it's the same phenotype, the same organization. And this is from Johan Smith lab. And you can see that you have in the GV stages the same distribution of chromatin status that are associated with the oocytes getting red and then maybe over. And I've put the picture of the apple to show you that maybe the most condensed form is, like in the animal, maybe not the best things to achieve. In the animal, we have the ability to recover oocytes at each stage when we want. We can even obtain the oocytes at the slaughterhouse. So therefore, we have a large capacity to document what's happening when the oocytes are at the different chromatin status, what happened where their ability to become embryos. So the first slide I'm showing you is the distribution. And what's surprising here is the distribution of the GV1, the one that are still transcribing RNA, are quite evenly distributed, even in larger follicle, larger than 6. The frequency of GV2, again, it's the same, and the same for GV3. So in the animal model, the transition for GV1 for GV2 or GV3 is about 2 or 3 days, and it's rolling constantly. So each follicular size will have a number of oocytes at each chromatin status. When we do IVM with those oocytes, and we look for blastocyst rate, we can see that the blastocyst rate with the GV1, when the chromatin is not condensed, it's pretty low. It's like 9%. When you go to GV2 stage, it goes to like 23%. And the GV3, it's not bad. The oocytes are not crippled yet, but you can see there's a tendency for these oocytes to be not better, but maybe even possibly a bit worse. Now, if I try to organize in a dynamic manner the distribution of those 3 chromatin status, and I'm going to go from early cycle to late cycles, like here when we start with the predominant. So we have follicles that are starting to respond to FSH over 3 millimeter follicles. And initially, if the FSH is maintained, they're going to remain in GV1. But if FSH goes down, once there's the dominant follicles, the oocytes will acquire LH receptor, and it will move into GV2 or GV3, or if it goes in early atresia, we also see the same progression from GV1 to GV2 and GV3 in the atretic process. When the follicle grow a little bigger and become recruitable by stimulation, the same thing happens. We have a GV1 initially, and if those cycles are not supported by extra FSH, only one follicle will become dominant, and the other one will go to GV3, and there's the one that will go in atresia will go to GV3 status. Now, when we go to one dominant, which start at 11 millimeter in human, then initially that transition of FSH supported to LH support will trigger the change in chromatin configuration. But if the follicle is not selected for ovulation or pushed into ovulation, it will go into atresia and again go to the same stages of GV2 and 3 within about 3 days. That's what we see in the late dominant or post-dominant. So if the follicle is not ovulated, all the follicles will start the atretic process, and then they will all move to GV3, and their quality will go down. And what we observe in animals, and probably it's the same in human, is aneuploidy at that time is going up. So for many, many years in the model we use, the bovine, when we collect ovaries at the slaughterhouse, we have all sorts of follicle from all sorts of animal. So we have a random population and we don't use stimulation. In that cases, and there's hundreds of publications, the rate of embryo you can expect is about 30 to 40%. So normally at any given time, you will have 1 egg out of 3 that will be at the right status, the GV2 status. And that's what is the distribution I showed you before. And not surprisingly, that's the rate of embryo we obtained. And it's not by luck, it's because of that status. So what we have in this type of heterogeneous population, some eggs are too early, the GV1. Some eggs are just at the right time of the plateau phase, they're GV2. And a number of eggs are early atretic, they're GV3, and they're not good anymore. So that creates a population where the oocytes will have different needs and will have different success in culture. Now, when we start to organize this information and we use FSH as a stimulation mechanism to create a growing wave of follicles, then we can have, as long as FSH is maintained, we can have GV1 even in the largest follicle that are observed, because the FSH will maintain that chromatin status. The follicle is actively growing, and the oocytes without LH receptor know it's not time to ovulate and will wait. If we keep giving FSH, we're going to keep having more and more of those GV1 oocytes in larger and larger follicles that are responding to FSH. But if you ovulate them at this time, in fact, the 1/9 will respond to LH, you will not have oocytes that are ready to be ovulated. Although they will ovulate, they will mature, but internally they don't have the right components. So you're going to have oocytes, even if they are metaphase 2, that will be coming from GV1 stages and will not have the highest capacity to become an embryo. So what we've done in animals to go around that is we give FSH a number of days, and then we synchronously stop FSH to create that switch from GV1 to GV2, and then we wait the right amount of time, which is about 60 hours, to get a maximum number of eggs that are at the right stages. And that's what we observe. We now do this process commercially in animal, and using that scheme of several days of FSH and then we stop, the population we observe is, even at different size, we're going to have the majority of the eggs that have reached the LH receptor level will all synchronize into the GV2 stages for the 60-hour period. And if we collect them and fertilize them, we're going to have from 70 to 80% blastocysts from those eggs. And although I'm saying there's no direct effect of follicular size, this is not exactly true. There's still better eggs coming from larger follicle, but it's also related at the same time as the size and timing after FSH arrest. So the oocyte has only a very small window to be efficiently good. If I try to summarize, this is a commercial data from the bovine IVF system, and if I try to summarize where is the best window for getting the best eggs, and it's when the follicles are larger than 8 millimeter, it means that they have LH receptor, and FSH has been stopped for about 60 hours. And then in that window, if we collect the follicles that are larger than 8, we have the average of 60 to 80% blastocysts coming out of this population. So how can this be applied to human IVM? Well, it's the same context, and it's obviously with the picture I've shown you in human, it's the same situation. So the best way to get good eggs in human as in animals is to create a population of dominant follicle. With FSH, you create a wave, 10, 15, and then you reduce FSH support and replace that by LH support in a timely manner. You create that switch, you induce that window of differentiation, and then you can recover GV stage oocytes between 2 or 3 days later. That will have a GV2 status where the capacity to go to the blastocyst stage following fertilization. Or, and that's often what's done, you trigger, because then you have created kind of a regular IVF wave, and therefore there is less benefit to do IVM unless there's specific hyperstimulation syndrome risk, and then you can trigger and recover the eggs at very high quality within 34 hours, but after this 2 or 3 days of low FSH. So in conclusion, the oocytes of quality rise only a few days before ovulation, and especially when FSH decreases. That creates the chromatin to start to condense and limits the time that the oocyte is going to be good before the oocytes start to become aneuploidic. So to harvest the best oocytes, the chromatin has to be condensed for about 60 hours or 2 or 3 days to ensure you have the maximal number of red apple in your population. You have no more greens and no yet rotten apples. That's what is probably the best scenario for these oocytes. And I'd like to acknowledge the CIHR for the support, and also the clinic in Ottawa who did the individual oocytes follicle aspiration that led us to understand what are the factors that are associated with the large follicle that leads to not so good oocytes anymore. And I would like to thank you for your attention.